Hi, I'm Lauren Perry, and today I'll be presenting my lab report for Physics 2211. In this particular experiment, I investigated the motion of an expo marker that is moving at the same speed without changing direction or simply at constant velocity. To do this, I placed an expo marker on a flat table surface and gently pushed the marker with little force, which allowed the marker to move across the table in a straight line. The system within this experiment is the marker itself. Its surroundings are everything else, such as gravity, the table, etc. After putting the video in Tracker, I was able to plot the marker's position at different time intervals, creating a graph of the motion and velocity of the marker from time 0 seconds to 1.33 seconds. I copied the data into my own graph to get the linear approximation with the equation y equals negative 26.689x minus 1.1694 and the correlation coefficient of r squared equals 0.9985. I then constructed a computational model to accurately describe my observations based on Newton's second law, or simply the momentum principle. Starting out with the starter code, I made sure to run the code while t was less than 1.33 seconds, in other words, to accurately depict the marker's movement versus time. Because I am measuring the marker at constant velocity, I made sure to tweak the fnet vector to 0, 0, 0 newtons. Next, I updated the velocity as the slope on the position versus time graph. So, in my equation, negative 26.689 is the slope, making my velocity vector negative 26.68900 meters per second. Similarly, I took the y-intercept in my equation and recognized it as my updated position of negative 1.169400 meters. Adjusting the code with this information, I ran the code almost exactly like the observed graph from my expo marker video. The purpose of this lab was to compare my computational model to the observations of the expo marker by constructing graphs to properly plot both the observed position versus time and the predicted position versus time on the same graph. Because my data was measured on the y-axis instead of the x, it made sense that both graphs would be constantly moving in the negative direction. However, a possible error could be routed from my use of the y-axis, but modifying only the x component of my computational vectors, although the data is the same. Now, what if I made the choice to flip the axes, as in making, in my case, the positive y and negative y axes interchanged? Swapping these axes would make the data much more difficult to interpret. For example, the y-axis would now represent position the x-axis would now represent position and the y-axis would represent time. But time doesn't change where you can plot a dependent variable on the vertical axis. Furthermore, the slope of the graph would represent the inverse of velocity, telling us how quickly time is passing for each unit of position, which is not the way to describe the marker's motion accurately. What does this mean? It is possible to say that there are multiple forces being added together to give zero net force. In fact, there are. In this case, gravity is in play by the weight of the marker acting downward, normal force, where the table exerts an upward force to cancel out gravity. Also, friction, where the friction between the marker and table resists motion, directing the force in the opposite direction that the marker is rolling. Finally, the applied force by the push of the marker going in the direction of the marker, canceling out friction. Therefore, all of the forces cancel out, giving a zero net force. Thanks for watching.